Swayam Prabha. Digital India. Educated India.
Let's get started today's lecture, and what I would like to do is continue with our discussion on second law of thermodynamics. But before that, I reiterate that the thermodynamic laws that we discussed so far are basically the product of human experience. So, what it is. So, before going into the other details, let me just mention the first one, that is the first law of thermodynamics, in this sense that first law of thermodynamics. So, it goes like this, that if we have a system and you operate the system in a cyclic process, then the heat gained by the system from the surrounding is equal to the work done by the system on the surrounding. So, let me write it down, that if a system operates in a cycle, then the heat gained by the system from the surrounding is equal to the work done by the system on the surrounding. So, what I am doing, I am operating a system over a cycle, and there is a heat in the cyclic process and work done by the system on the surrounding in that cyclic process. So, when we write it formally, then we write W cycle equal to Q. This way of representing the first law actually eliminates the mention of the internal energy, because the system comes back to the initial position. So, this is a convenient form of the first law that we would like to proceed with this one. And you know that the Q of cycle means that the system operates over a cycle, and when it is connected to to reservoir, not mention how many reservoirs are there. So, in general, it may be there are several reservoirs with which the system is connected. So, it is possible that this Q cycle is the in total the heat gain or loss or anything, that Q cycle is composed of several parts, the Q1 plus Q2 plus, this means that the heat is drawn from the, this Q1 is the heat drawn from the first reservoir, the heat drawn or heat exchange with reservoir 1. This is the same with the reservoir 2, and so on. So, Q cycle is a composed of several such quantities, and so this is basically the first law. And the second law tells us that if your Q, all Q2, Q3, Q4, second law tells us, there comes the second question, the second law. This tells us that if Q2, Q3 are all 0, that means that if you have this Q cycle is composed only of Q1, then W cycle equal to Q1. This is the first law, but W cycle is less than or equal to 0. That means that if this is the first law, that gives you the conservation of energy, and when the heat exchanged with several reservoirs 1, 2, 3, etc., you have a total Q cycle. And if I say that the system is connected only to a single reservoir, single heat reservoir, then the work done by the system is ultimately less than or equal to 0. So, when it is equal to 0, if for the reversible process, W cycle equal to 0, for irreversible process, W cycle is less than 0. So, this is a more concrete form of the second law, or in words we write it that if a system operates in a cycle and connected to a single heat reservoir, attached to a single heat reservoir, then the work done by the system, better we would like to write it in this way, then it cannot produce any positive amount of work. So, that is clearly what we have said in this equation that if your W cycle is equal to Q1 only, then W cycle must be less than or equal to 0. Hence, it means it is never positive. Then it means that if a system operates in a cycle and connected to a single heat reservoir, then it cannot produce any positive amount of work. So, that is another statement, the same kind of statement that we are actually giving in a different form. So, that is in a nutshell what second law is. Now, the point is that if it is so that I cannot really produce a positive amount of work. So, what should we do? Then it is better to add additional heat bath, like instead of Q1, take at least one heat bath to it. So, Q cycle is composed of not the single heat bath. So, I do not like the, so what is, we have seen that you have a system and it is connected to a heat reservoir at a temperature. This is connected, say, to a heat reservoir at a temperature T, and you are getting some W over a cycle. It is Q cycle, it is just Q cycle equal to Q1, then W cycle is less than or equal to 0. That is in a schematic form. I have written the same thing. Now see, the system is operating over a cycle, and as well as it is connected to a single heat reservoir at temperature T. So, what I do here, so instead of taking only one heat reservoir, let us try with two heat reservoirs and see whether I can make this W cycle positive, because it is an impossibility condition that we cannot do this thing. It is impossible to produce a positive amount of work with a single heat reservoir. So, that is not sufficient. So, what we would like to do, we connect now connect the system to two heat reservoir. That means I connect the system to two heat reservoirs. Say I have an heat reservoir 1 and another heat reservoir 2. I connect this. This is I call Q1. This is I call Q2, and it is at a temperature T1, at a temperature T2, and since there are different temperatures, then W cycle equal to Q cycle equal to, that is equal to Q1 plus Q2. So, we take at least two reservoirs. So, this should be our scheme, and we need to have, we can get some, let us see whether this W cycle is really positive or not. So, that was the attempt that we should do that and see and utilize that if I connect the system to two reservoirs at different temperatures, because if they are same, nothing will happen, because it's the same temperature, so same heat. So, you will have only Q1. So, effectively they will have different temperatures. Suppose T1 for our, by construction I take T1 greater than T2. I construct the system which is connected to two heat reservoirs, one at a higher temperature, one at a lower temperature. I do not know the signs of actual sign, algebraic sign of Q1 or Q2, but I see that there is a Q cycle, a W cycle, or the work that is coming out of the system, whether it is positive or not. So, I want a positive amount of work to be done by the system. We call this a machine, an engine. So, let us try with this. So one such device was first attempted by CARNOT. So CARNOT took this kind of model where he actually connected the system to two heat reservoirs, one for the let us see what CARNOT or the CARNOT 1824, around that period. He was a French engineer and he devised an engine where he connected a system to two heat reservoirs. And his scheme is the following. So his scheme is the following, that Carnot scheme. So he took that a system with which can be described by pressure, volume, temperature, and then consider the first point when it is a P1, V1, and T1, the system is allowed to expand. The system is allowed to expand from, say, P1, pressure P1, volume V1 at a temperature T1, right at this point. So this is an expansion. The first stage is an expansion. This is expansion. In expansion, and I keep, so this point is P2, V2, T1. That is the isothermal expansion. The temperature remains same all throughout. That means I connect the system to a heat bath at a temperature T1 and expand a gas, any gas or something, that in that way. So that we call isothermal expansion. For P1, V1, T1 to P2, V2, T1. Next step, what we do, another expansion process, but it is completely adiabatic. So adiabatic are stiffer curves. So I go from P1, P2, V2, T1 to P2, P3, V3, T2. So it is, that step is called adiabatic expansion process. And I go from P2, V2, T1 to T3, V3, T2. So temperature is changed as it moves adiabatically from P2, V2 to P3, V3, and the change in temperature is T1 to T2, because then it is under adiabatic expansion. Now we compress the system once again to come back to this initial state, so that I will complete a cyclic process. So since it is a cyclic process, and at the same time I will carry everything in a reversible, under reversible conditions. So I will try to carry out a reversible cyclic process in this way. So I return to this point by isothermal compression from P3, V3, T2 to P4, V4, T, T2. So I come back to this point, it is come to this point, that is P2, P4, V4, T2. So T2 remains T2 over this isothermal compression. Then I finally move to the initial state, and this is again by adiabatic compression, and that is P4, V4, T2 to P1, V1, T1. So this is the total process which is being carried out reversibly over a cyclic process. So it is a cycle, and it is called the CARNOT cycle. So in this process, what is going on? So let us first apply the first law of thermodynamics and see what are the things we can derive out of it. So by application of the first law, for this step, we see that delta for the first step, it is delta E1, first step is basically Q1, because the system is connected to a heat reservoir with which can exchange heat with Q1, and this is as a temperature T2 at a T1, and there is another heat reservoir, it is connected to another heat reservoir Q2. So if it is connected to another heat reservoir at a temperature T2, then first one, it is Q1 is the amount of heat given in the system, then it is W1, Q1 minus W1 for the first step. Then delta E2 is an adiabatic process, so there is no heat exchange, so it is just minus W2, Q term is 0, second step, and delta E3, third step, it is again an isothermal step, it is connected to a second heat reservoir with which it extends Q2 amount of heat and minus W3, that is the third step, and the final step for returning to the initial step is minus W4. So it is the fourth step. So if I sum over all the steps on both sides, then I have a summation. Let us take E1 plus delta E2 plus delta E3 plus delta E4, that is equal to cyclic integral over dE, and that is equal to 0. That means the sum over all these terms are 0. So that means the right hand side, if you sum up, then what happens? It gives you that Q1 minus W1 plus minus W2 minus Q2 minus W3 minus W4, that is equal to 0. So it is Q2 minus W3, Q1 minus W1 minus W2 minus W4. So this means it is W1 plus W2 equal to Q1 W3 plus W4 equal to Q1 plus Q2. So I have a W cycle equal to Q1 plus Q2, that is the Q cycle. So the first law is kept intact in the entire reversible process that we have carried out over a cyclic reversible under cyclic reversible condition. So, this is the basic thing that we have learned now. Now, we are still not sure about what are the signs of this Q1 and Q2. But before that, if we try to define another quantity, that if we write the efficiency I can call some eta, and that is basically W cycle that I want from the system, and by giving Q1 hit in the first step, that is the Q1. So that is what is W cycle? W cycle is basically Q1 plus Q2, that is divided by Q1. It is 1 plus Q2 by Q1. So efficiency is a quantity that can be defined in terms of the two heat quantities, that Q2 and Q1, which are being exchanged. Q1 or Q2 are the heat that are being exchanged with the two heat baths at temperature T1, kept at a temperature T1 and T2. And so we have no idea still now what are the signs of these Q1 and Q2. So let us check how to get the signs of these quantities, signs of Q1 and Q2. So next question is, what are the signs, algebraic signs of Q1 and Q2? That is an important question, but because the efficiency will depend on the sign of the heat transactions. So how to deal with this thing? So the point that, so for this, what we do, we come back to the original scheme that we have been talking about, and this scheme is scheme that we have already written, that this is T1 this is the system, and this is a heat, this is W of cycle that the system produces, and it is at a thermal bath at the temperature T1, this thermal bath at the temperature T2. Let us assume that the both have the same signs. We start from the condition that, let us first assume T1 is greater than T2. That means this T1 is a high temperature bath and T2 is a lower temperature bath. And we assume Q1 and Q2 are positive. Both have the same sign and both are positive. If it is so, when I draw the line like this, it means that the system draws heat both from T1 as well as from T2. So the first law tells us, the first law tells us W cycle. So this is Q1 and this is Q2, Q1 plus Q2. So the system draws heat both from this reservoir and also from the lower reservoir, lower temperature reservoir. Now, if we connect the system by a heat conducting rod in such a way that the heat that is being transported from the lower bath, lower temperature heat bath to the system gets nullified. That means I put a temperature here, I connect the two things and I transfer the heat, Q2 heat, from the high temperature to low temperature by connecting a rod. So, for the composite system, you see after connecting the heat bath to the by a heat conducting rod, we transfer Q2 amount of heat from T1 bath to T2 bath. This leads to a situation like this: W cycle equal to Q1 plus Q2, both are positive by construction. Then we subtract Q2, then it is just Q1. And because it is attached to a single heat bath, W cycle must be negative or 0. So it cannot be positive. But we assume from the beginning that we also assume here, I forgot to mention, the assume Q1, Q2 are positive, and also W cycle is greater than 0. So with these with this given condition, we see that there is a contradiction, that Q1, that Q2 terms gets cancelled out and I have only Q1. So W cycle is effectively connected to a single heat bath, or the system is connected to a single heat bath, and that means we have only, so W cycle must be less than or equal to 0. So this violates our initial assumption that W cycle is greater than 0. So this contradicts this one. So because we have only Q1, so both of them cannot be positive. So one must have opposite sign. So W and Q1 and Q2 cannot have same sign. So Q1 and Q2 cannot same sign. So what we can, since they cannot have same sign, so if Q1 is positive, then Q2 is negative. So I write this condition that, so I can write eta equal to 1 plus Q2 by Q1, and that is equal to 1 minus Q2 by sorry, I have Q1, Q2. Q1 is positive. Okay, is positive. Okay, Q2 negative. So I can write it formally in this way. So, so I can see that there is a ratio of the quantity of heat that is being exchanged with the system, and they have some signs that must be maintained. Otherwise, that will be that will violate again the second law. So, so this arrangement is quite fine now, that we for a two temperature heat bath with two. So when the system is connected to two different heat baths at different temperature, we can certainly construct an engine like this, whose efficiency is given by 1 minus Q2 by Q1. So stop here, and in next lecture we will proceed further with the other details of this engine. So thank you all.